Good afternoon. Today is October the 11th, and we're going to be covering section 3.9 in your textbook. We're going to be covering exponential and logarithm functions and derivatives of exponential and logarithm functions and a technique of differentiation called logarithmic differentiation. Before we get started in any of that, I want to make sure that you know, and I have sent an email out, or I will be sending an email out later today, but exam 1 grades are ready and are uploaded to D2L. So if you can go to D2L and you can look for your grades in the grade book there, and you ought to be able to find your exam 1 grade as well as your homework grade there. And if you want exam 1, the graded version of exam 1 to be returned to you, if you will email me, then I will respond to your email and I will include the graded copy of exam 1 as an attachment. But you must email me in order for me to do that. So I'll be looking for your emails as far as getting your graded exams back. Now what we're coming out of right now in class is we started talking about derivatives of functions that are inverses. So we have taken care of functions that are inverses, first of all, talked a little bit about inverse functions in general. And then we looked at derivatives of inverse functions and how the derivatives are connected. And then we started looking at some specific examples of derivatives with inverse functions. We looked at the inverse trig functions and their derivatives. And so we covered that material last time. And so today we're going to be moving on and talking about exponential and logarithm functions and kind of going that route and looking at derivatives there. So first of all, exponential functions are basically functions that are in this form: f of x equals b raised to the ax power, right? And it makes the function gets to be exponential, quote unquote, because there's a variable in the exponent. And logarithm functions are functions that can be written in this form: f of x equals logarithm base b of x, like that. And so what we want to do is look at some general things about these kinds of functions. First of all, just to review and remind you of a few things that you should have seen in an algebra class before. And then after we've kind of taken care of the highlights of that, then we'll move on and actually look at calculus as far as logarithm functions and exponential functions. Now the base for an exponential function, f of x equals b raised to the, and let's just say b raised to the x power. That base, there are some restrictions on it. It must be greater than 0. The base has to be positive, and the base cannot be equal to 1. You wouldn't have an exponential function if the base was 1. All right, so the most important exponential function that we look at is f of x equals e raised to the x power. And we'll talk more about the origins of e and everything later, but e, remember, is an irrational number approximately equal to 2.71828, right? And its decimal goes on forever. That exponential function is the most important one that we will have, and it's the most common one to find in applications. Recall that the graph for an exponential function like this, in this form, is what we call a growth curve. And in this case, our exponential function goes through the point 0, 1, and it goes through the point 1e, or 1 about 2.7. So 1e, and you have this growth curve that looks like this. Exponential functions are very fast rising graphs. The domain for this function is all reals. It's defined for all real numbers, and the range is everything greater than 0. Also notice that there's a horizontal asymptote on the x-axis. In other words, where y is equal to 0. You have a horizontal asymptote. All right, as far as limits go, the limit as x goes to infinity for e to the x is equal to infinity. That's very clear from the graph. As x gets larger and larger, e to the x gets larger and larger. And the limit as x goes to negative infinity for e to the x is equal to 0. Right? As x gets to be a larger negative number, e to the x gets closer and closer to 0. And that just obviously refers back to the horizontal asymptote that you've got on the graph, that there's a horizontal asymptote there on the x-axis. All right, now in a more general setting, for exponential functions, more generally, functions in the form f of x equals b raised to the x power. If b is greater than 1, those graphs are all growth curves. If the b value is greater than 1. So I'm not really sure why I put the axis there like I did. Let me erase that real quick and put the y-axis kind of lining it up with the grid right here. All of these graphs, if b is greater than 1, go through 0, 1, and then they all go through this point here at 1b. Whatever the base is, when x is 1, you'd get the y value to be b. And if b is greater than 1, then that point would be higher than the point at 0, 1. And so you get, in general, all of these graphs are growth curves. On the other hand, if b is less than 1, so if b is between 0 and 1, then the base is less than 1, and that graph goes through 0, 1 also. But now when it goes through 1b, b is less than 1, and so that graph is a falling graph. And when x is negative 1, you'd have 1 over b, or the reciprocal of b, and if b is less than 1, its reciprocal would be greater than 1. And so you've got a graph, still goes through 1b right here, but now you get a graph that's a falling graph, similar shape, but a falling graph, and this is sometimes called a decay curve. All right, so just remember that in general, exponential graphs are either going to be growth curves or decay curves, and depending on what the base is. And in particular, the most important exponential function we see is f of x equals e raised to the x power. Now, on the next screen, let's see, if f of x is equal to e to the x, then the inverse for this function is the natural log function. F of x equals natural log x. And remember that natural log x is simply an abbreviation for logarithm base e of x. And this is the inverse of the exponential function e to the x, right? So if we have our graph for e to the x, looks like this, goes through 0, 1, and it goes through 1e, 1 about 2.7. Here's our graph for e to the x right here. Then its inverse, which is the natural log graph, goes through the point 1, 0, and e 1, and looks like this. And that's our natural log graph. That's natural log x. Remember that since they're inverses, these graphs would be symmetric around the line y equals x. Right? We have symmetry around that line right there. The natural log graph, so if you're talking about f of x, or let's say just in general, g of x equals natural log of x, that its domain and range switch around from the domain and range of e to the x. So the domain for the natural log function is from 0 to infinity. And notice there's a vertical asymptote on the y-axis. In other words, where x is 0. And the range is going to be from negative infinity to infinity. If you talk about the limit as x goes to infinity for natural log of x, it's equal to infinity, though that's misleading because the graph rises very, very, very slowly as x gets large. And you can't talk about the limit as x goes to negative infinity because those values are not in the domain for the natural log function. So we talk about the limit as x goes to 0 from the right for the natural log of x, and that would be equal to negative infinity. And that's where we've got the vertical asymptote is at 0 for the natural log function. Because the functions e to the x and natural log of x are inverses of each other, we have inverse cancellation properties. And so the inverse cancellation properties look like this, that e to the natural log of x is equal to x, and the natural log of e to the x is equal to x also. And those are the specific versions of inverse cancellation for these functions. Also recall that for the logarithms that you have some specific values here. You have the natural log of 1 is equal to 0. The natural log of e is equal to 1. Right, and those are just the reverse of e to the 0 equals 1, or the inverse of e to the 0 equals 1, and e to the first is equal to e. Right, those are just kind of the inverse properties for natural log and e to the x, like that. Also, let's see, recall then that you can have logarithms with other bases also. So if you're looking at more generally, f of x equals log base b of x in general, one way you could talk about a problem like this or a logarithm like this, kind of an algebra way of talking about it, is that this simply represents the power you raise b to get x. So if you have, for example, logarithm base 2 of 5, this is the power, this represents the power you raise 2 to get 5. So if this is equal to y, writing that phrase out in symbols, that would simply say that 2 raised to the y power is equal to 5. Right, and these are equivalent statements right here, and you certainly should be able to walk yourself back and forth between a logarithm statement and an exponential statement. So in general, you can write that y equals log base b of x is equivalent to b to the y is equal to x. It represents the power you'd raise b to get x, and so notice y is the power here. The logarithm is equal to the exponent. Logarithm is equal to the exponent. So for the natural log, then if you have y equals natural log of x, then the equivalent form for that exponential form would be e to the y is equal to x. So that's definitely something you ought to be able to walk back and forth for them. And then the common log, remember that common logs are base 10 logarithms, and the abbreviation for a base 10 logarithm is y equals log, y equals log x. Log x is the abbreviation for logarithm base 10. And so the equivalent exponential expression or exponential statement would be 10 to the y is equal to x. You ought to definitely be able to go back and forth between those problems like that. All right, so I'm going through properties of exponential and logarithms functions very fast here. This is stuff I'm assuming that you've seen before and have encountered before in other classes, and I'm just kind of refreshing your memory about some of this. Finally, there's some properties of logs that are important for us as calculus students, definitely. you have the power property or power law for logarithms that says you have logarithm base b of x raised to the a power, that's a times logarithm base b of x, that a power can be written in front of the logarithm as a factor. And you can look at the basis for all these laws, certainly in terms of rules of exponents, that these all are just restatements of rules of exponents, because logarithms represent exponents. The product rule is that logarithm base b of x times y is logarithm base b of x plus logarithm base b of y. Right? The log of a product can be written as the sum of two logarithms. And then finally, the quotient rule for logarithms. Logarithm base b of x over y is equal to logarithm base b of x minus log base b of y. And remember, those last two rules, especially, you can see their basis back in exponent rules, because when you multiply exponent expressions together, what do you do with the exponents? You add them. And so notice down below, when we have the log of a multiplication problem, what do? I add the logarithms. And then when you have a division problem with exponents, what do you do with the exponents? You subtract them. And so notice that's the quotient rule for logarithms, that if you have the log of a division problem, you subtract the logarithms. Why do these rules mimic or parallel rules of exponents? Is because, remember, logarithms represent exponents, right? So when I wrote these statements at the top, you can always think of it that way, that logs represent exponents. Where logarithms are always equal to exponents. All right, certainly the power rule has its version here also, that when you have x to the a raised to the b, that what do you do with those exponents? You multiply them. Right, and so that's what we've got over to the side when we've got logarithm base b of x raised to the a power. You're actually multiplying the two powers together. That logarithm base b of x represents a power, and the a represents a power, and you're just multiplying them together. Sure enough, that's exactly what you've got right there. All right, so like I said, a very, 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 very fast kind of summary of properties of logarithms that we wanted to look at, and properties of exponential functions. So what we want to do now is we want to look at derivatives, and we're going to start with logarithms. We're going to start with derivatives of f of x equals not just any logarithm. We're going to start with natural log x and look at that function and its derivatives. Now, if you recall, now the way we kind of going to get the handle on this is going to be kind of a different way to get a little bit at what the derivative of f of x equals natural log x. And so we're going to fill in the blank here with f of x. If f of x equals natural log of x, then f prime of x is equal to, and that's what we want to do, is figure out or get some idea of what that function might be. Now, if you use using the alternate definition for f prime of x, if we use the alternate definition for f prime of x, then you've got that f prime at a specific value, at f prime of a, and that's what I should have written right here, is f prime of a. F prime of a would be the limit as x approaches a of f of x minus f of a over x minus a. So remember, that's our definition for a logarithm. I'm sorry, for a derivative at a point. And so in our particular problem, if our function here is natural log x, then this for our specific function, so for f of x equals natural log x, then f prime at a would be equal to the limit as x approaches a of f of x, which would be natural log of x, minus f of a, which would be natural log of a, and that'd be all divided by x minus a. So you get that expression right there. And so f prime of a would be equal to the limit as x approaches a. In the numerator, I've got the natural log of x minus the natural log of a. And I could use the quotient rule for logarithms to combine those. And so that'd be the natural log of x over a over x minus a, like that. So now what I've done, or what I've kind of started doing here is, what would be the derivative for our logarithm function? Remember, f is a logarithm function. What would be the derivative at 2, for example? So that would be the limit as x approaches 2 of the natural log of x over 2 over x minus 2. And, we could continue on with this. That f prime at 3 would be the limit as x approaches 3 of the natural log of x over 3 over x minus 3. And we could continue on like that. Now, so what I've done is I've actually looked at these problems numerically, and I kind of built a little table of values here. And I used my graphing calculator to actually kind of calculate these values. And so for f prime of 2, right, remember we're looking at the limit as x approaches 2. Now I just use values a little bit bigger than 2. You could use values a little bit less than 2 also. You're going to get the same kind of values here. Same kind of thing's going to happen. But if x is 2.1, then the limit is going to be 0.4879, approximately, right? That goes on like that. So all I did was I substituted 2.1 in to my function natural log of x over 2 over x minus 2, and I get 0.4879. And then I put in 2.01, and my calculator gave me 0.49875. I put in 2.001, and for that function right there, and I got 0.49988. Finally, I put in 2.0001, and I got 0.4999. Let's see, I got 3 nines there, and then 875. And what appears to be true here, that that this particular limit, which remember is equal to f prime of 2, that f prime of 2 is the limit as x approaches 2 of the natural log of x over 2 over x minus 2, and that appears to be equal to 1/2, right, based on my table of values here. So all I'm doing is evaluating a limit numerically by substituting in values into the function and using values that get closer and closer to my limiting value. All right, so now I went through and used my calculator and did the same thing for 3. So what you're doing here, again, making a table of values. And now what am I going to do? I'm going to pick x values closer and closer to 3. So it might be 3.1, 3.01, 3.001, 3.0001, like that. And we substitute those into that function, and we see what the corresponding y value is. So let's see. So I put in 3.1, and I get approximately 0.3279. I put in 3.01, and I get 0.33278. Put in 3.001, and I get 0.33328. And then finally, 3.0001, and I get 0.33327 ... So what appears to be true here for f prime of 3? For f prime of 3, where f, remember, is our logarithm function, you get the limit as x approaches 3 of natural log of x over 3 over x minus 3. And that appears to be, from our table, 1/3. Right? So that's our first two values. So we could continue on like this. I'm going to do one more. We're going to look at f prime of 4 in this case. So that would be the limit as x approaches 4 of the natural log of x over 4 over x minus 4. Remember, they're all going back to this, our calculations here on this page. We're using this statement that f prime of a is this limit right here. And remember what f is. F is the natural log function. And so we're evaluating numerically the derivative of the natural log function for some specific x values to see if we can see something that's happening here. All right, so in our chart, here's x, here's y, and we'd have x is 4.1, 4.01, 4.001, 4.0001. And I'd certainly, ask, it would be good for you to look at these kinds of things in your calculator yourself and kind of explore this on your own also. Okay, so for 4.1, we're getting approximately 2.4693. For 4.01, we get approximately 0.24969. For 4.001, we get approximately 0.24997. And finally, 4.0001, in fact, my calculator just rounded it to 0.25. And so what are we getting here? It appears that f prime of 4 apparently is about 0.25, right? Or 1/4. So in fact, notice what it appears to be true here. It appears that if f of x is equal to the natural log of x, then f prime at some specific value, a, appears to be 1 over a. And so what are we getting here? That in general, then, what appears to be true? In general, we have that if f of x is the natural log of x, then f prime of x is 1 over x, that the derivative of the natural log function is the function 1 over x. And x obviously clearly has to be a positive value here. Now certainly you could look at the graphs of these functions on the same set of axes if you wanted more evidence. We've looked at some numerical evidence that this relationship is true. If you wanted to look at some graphical evidence that this relationship was true, you could look at the graph of the natural log function. We know that this is the graph of the natural log function right here. So that's natural log x, and that's our function f. And we're saying that f prime of x is 1 over x. So f prime of x, the function 1 over x goes through 0, 1, goes through 1, 1/2, goes through 1/2. Not exactly like that, but you're getting values like this. Here's 1 over x. Yeah, at 1/2 it's 2, and so on. And this graph appears to be f prime of x, which is equal to 1 over x. Now, does that make sense that this is true? Well, look at the tangent lines on f of x equals natural log of x. Right? This tangent line, first of all, at the point 1, 0, is saying the green graph is the derivative, and what's the y value there? The y value is 0, 1. So what are we saying there? That the slope of the tangent line for natural log of x should be equal to 1 at that point. That certainly appears to be true. And then what about tangent lines as we progress further on down the graph? These should get shallower and shallower. They should have smaller and smaller slopes, slopes that are closer and closer to zero. And look at the green graph. As you proceed on to the right, the green graph is getting closer and closer to zero. And finally, values way over towards the asymptote. What's happening there? Those tangent lines are all very steep, and so their slopes should be very large numbers. And if you look at the green graph gets to be very large. The y values get to be very large the closer you get to the y-axis. So this is nice graphical evidence that this derivative that we've just written down is actually a true statement. That if f of x is natural log x, then f prime of x is equal to 1 over x. So let's go ahead and shade that, because that's an important first step right here for our derivative, that the derivative of the natural log function is the function 1 over x. We've got some nice numerical evidence that it's true, some nice graphical evidence that that's got to be true also. All right, and then if you extend this rule, using the chain rule, we have this statement that if f of x is the natural log of u of x, the natural log of some function of x, then f prime of x is equal to 1 over u of x, that's what we just derived, or just found some evidence for, times u prime of x. That'd be the derivative of the outside times the derivative of the inside using the chain rule. And the way most students remember this, they simply write it this way, that f prime of x is simply going to be u prime over u, right? And that's our derivative for a natural log of u right there. If f of x is the natural log of u, then f prime is u prime over u. Now, if you want to go ahead and extend this property to other base logarithms, so other base logs, so in other words, f of x equals log base b of x, then the first thing you would probably want to do is use what we call the change of base formula for logarithms, which we didn't write down before. But to remind you, the change of base formula goes like this, that logarithm base b of x is equal to the natural log of x divided by the natural log of b. That's a specific version of the change of base formula. And that's a way of taking a logarithm, a base b logarithm, and changing it to a base e logarithm, a natural log. So if f of x is equal to log base b of x, right, then we would write that, first of all, using the natural log as a natural log of x over the natural log of b. And you might write that as 1 over the natural log of b times the natural log of x. Now, b is a constant, so the natural log of b is also a constant, right? And so that 1 over the natural log of b is a constant also. So in other words, that doesn't affect the derivative at all. It just comes down for the ride. And so f prime of x would be 1 over the natural log of b times 1 over x, right? That the derivative of natural log of x would be 1 over x, and then you get that 1 over natural log of b in there also as a factor. So that derivative actually has an extra factor in it, basically, is the way to look at it. So to summarize, and then we will look at some specific examples of differentiation here. But to summarize here, we have that if f of x is the natural log of u, some function of x, then f prime of x is u prime of x over u of x, right? And if you look at a more general logarithm, f of x equals logarithm base b of x, right? Some general base, then f prime of x is going to have this extra factor in here, 1 over the natural log of b times u prime over u. Right? So it just has that extra factor in there is all you're getting. By the way, all these properties are certainly written out for you in your textbook, in our OpenStax textbook, and these properties are written in section 3.9. So look at section 3.9 in your book if you're looking for these properties kind of written out. All right, so let's go ahead and look at some examples then. Mostly we're gonna look at the natural log function, but we will look at some other logarithms, other base logarithms too, at least a little bit. All right, so as an example, let's start off here with something pretty straightforward. If h of x is the natural log of 2x squared plus 1, right? So this is our u prime over u property we were just talking about, right? That if y is the natural log of u, then y prime is u prime over u. So in this problem, our u is 2x squared plus 1. So h prime of x would be u prime over u. It would be 4x over 2x squared plus 1. That's our u prime is the 4x. Our u is 2x squared plus 1. And there's our derivative, 4x over 2x squared plus 1. So that would be the derivative of the natural log of 2x squared plus 1. All right, the next problem, let's say we have f of x equals x squared times natural log of x. Now this is something I needed to talk to you guys about as a class. Definitely, as I was going through and grading your exams, a lot of you did need to pay more attention to what the form of the function is when you're differentiating it. This is a multiplication problem right here. And because it's a multiplication problem, to find its derivative, you have to use the product rule to do this. And so I was getting too many people on this exam 1 overlooking multiplication and division problems and how that relates to a product rule and quotient rule, things like that. So you really need to pay attention to that. So this is a product rule problem for differentiation. So f prime would be the first function times the derivative of the second. And on this problem, I'll actually write that out. The derivative of the natural log of x plus the derivative of x squared times the natural log of x, right? You're taking a derivative of a different function in each term. So f prime of x would be the x squared times the derivative of natural log of x, which we've now said is 1 over x, plus the derivative of x squared, which is 2x, times natural log of x. And then you could simplify a little bit. The x squared times 1 over x is x. Then you get x plus 2x natural log of x. Definitely not uncommon to see the author of various different textbooks simplify this by taking out a common factor of x, and you're left with 1 plus 2 natural log x, like that. And you'll even get books that'll write this, that'll take that 2 natural log of x and write it as the natural log of x squared. Bring that 2 up as a power, using the power rule for logarithms. Now, what I would prefer is, I don't care about that last part at all, but I really do want you to look for common factors, and that would be my preferred form right there. And that's the way I'd like to see you do it, is at least take out common factors there, and but don't worry necessarily about writing that logarithm like I did right there. All right, next example. So we're looking at a ton of examples here because there's lots of different situations that you need to be aware of. So we have y equals the natural log of the square root of x squared minus 4. Now, the square root of x squared minus 4 is, the same thing as x squared minus 4 to the 1/2 power. And so if you're going to differentiate that's my u in this case. So if you're going to differentiate that, you're going to be using the chain rule to do that. Well, there's a way to simplify this process and this problem quite a bit. And so in general, when you've got a logarithm, see if you can simplify the logarithm first. See, so like in this problem, the natural log of x squared minus 4 is really the natural log of x squared minus 4 to the 1/2 power. And then you have a power rule for logarithms that says you can bring that 1/2 down in front as a constant factor. And so our natural log of square root of x squared minus 4 could actually be written as 1/2 times the natural log of x squared minus 4. That's a big help in this case as far as differentiation goes. So you have 1/2 natural log of x squared minus 4 is my function. And so y prime, well, that 1/2 just comes down for the ride. And then you're taking the derivative of the natural log of x squared minus 4, which would be u prime over u. This is my u now, is simpler than it started out to be. And this would be u prime over u. Much simpler than it was. So simplifying first can really be a big plus and help you quite a bit as far as differentiation goes for logarithms. Also, the 2's divide out at the end, and so you just end up with x over x squared minus 4 when you're all said and done there on that problem. All right, so simplifying first, simplify the log first. Keep that in mind, that is something you should always be thinking about, is can you simplify the logarithm first? If you can, then try to do that to make the differentiation easier in the problem. All right, so let's look at a couple more examples here. So if you have y equals the natural log of t times t squared plus 3 quantity cubed, like this, then this would be a classic example. Notice, by the way, and a lot of times I won't write these restrictions down, but logarithm functions come with restrictions frequently because remember, you can only take the log of a positive number here. So this function carries with it the restriction that t must be greater than 0 because of that factor of t that's in that function, right? You couldn't use a t value less than 0 in this problem because you'd get values that would not be in the domain of the logarithm function. All right, so simplify first before you differentiate. This problem definitely carries some simplification stuff that you can do very easily. First of all, you have the logarithm of a product. So write that as the sum of two logarithms, the natural log of t plus the natural log of t squared plus 3 cubed, like that. And then the second logarithm is a log of a power, so bring that 3 down in front as a factor. And so if you write the function like that first, you've made the differentiation oh so much easier. And so y prime in our problem would be 1 over t, that's the derivative of the natural log of t, plus 3, that's a constant factor, so it comes down for the ride. And then the derivative of t squared plus 3, that would be my u, is the t squared plus 3. And the derivative would be u prime over u, like that. And so y prime would be 1 over t plus 6t over t squared plus 3. Now, you ought to be able to, I mean, you are calculus students after all, so you ought to be able to get a common denominator on fractions like that. And so the second fraction you'd multiply by t over t, and on the first fraction you'd multiply by t squared plus 3 over t squared plus 3. Right? And so when you combine these two fractions, you'd get t squared plus 3 plus 6t squared over t times t squared plus 3. And so that would give you 7t squared plus 3. Make that t a little bit neater here. 7 7t squared plus 3 divided by t times t squared plus 3. And that would be our derivative for this function. And I'm not going to, there are times when getting a common denominator would be it's kind of unreasonable because it's such a mess to do. So I'm not going to go nuts with that, but you ought to be able to take two fractions like that and add them together by finding a least common denominator. I don't have a problem with asking you to be able to do that. All right, another example. Let's say we have g of x is the natural log of the natural log of x. Now remember, this is the natural log is a function. That's a function symbol there. It's function notation. That's not a multiplication problem. It's not the product rule. Don't think that that's the natural log of or times the natural log. That is the natural log of the natural log. And so that's a function of a function. And so this is a chain rule problem. Right, where the natural log of x, that's my u. That's my inside. So g prime of x would be u prime over u, right? And what's u prime? If u is the natural log of x, u prime would be 1 over x. So this is 1 over x over u, which is the natural log of x. And that's the derivative, is 1 over x over the natural log of x. And usually you'd see that written more simply as 1 over x natural log of x. Not a hard derivative, but it's a pretty simple statement overall, but it can throw people off because it doesn't look, kind of, it does, when you see the natural log of the natural log of x, it kind of throws people off a little bit. All right, so the next problem I want to look at, you're going to wonder at first why this is in here. You have f of x is equal to x cubed times x plus 4 squared times x minus 5 to the 4th power. And I want to find f prime on this problem. Now you may wonder why that's in here, because that is not a logarithm function at all. But I want you to think about what you would need to do here to differentiate this function. Is you'd have to use the product rule to differentiate it, because it's a multiplication problem, and it's kind of a gross product problem, right? This is a gross product rule problem. Because, it's a mess. You've got 3 terms. You have 3 factors, so you're going to have 3 terms. You have to differentiate a separate factor in each term. You're going to have the chain rule in there. It's just kind of a mess to do. I can use logarithms to make this kind of problem simpler. And when I say make this kind of problem, I can make the differentiation simpler in this problem significantly. What you do here is you first write this as y equals x cubed times x plus 4 squared times x minus 5 to the 4th. And then I take the log of both sides of the equation, and I'm going to use the natural log, definitely use the natural log. So take natural log of both sides. First of all, that's allowed because the natural log function's 1 to 1. Because it's 1 to 1, you know that if 2 numbers are equal, then their natural logs have to be equal also. So this is a legitimate statement here to say that the natural log of y is equal to the natural log of x cubed times x plus 4 squared times x minus 5 to the 4th. Now one thing is that you need to watch for is notice this is an explicit function that we started with. But when you take the log of both sides, now you've got an implicit function. And so we're going to have to use implicit differentiation here. Now the implicit differentiation is not going to be that big a deal, but you have to be aware of the fact that that's what you've got. Now on the right side of the equation, what do I have there? I have the natural log of this multiplication problem. So this would be the natural log of x cubed plus the natural log of x plus 4 squared plus the natural log of x minus 5 to the fourth, right? Because this is a log of a multiplication problem. I'm just using the product rule for logarithms to write that out as a sum. And then I've got the power rule for logarithms. And I can bring those powers down in front as factors, like so. And those are constant factors, so those don't affect the derivatives. And so now I differentiate both sides. Now, when you differentiate both sides, you have to be careful. Now, the right side is easy. The right side just has x's in it, and so that's really explicit. And you just use the properties for logarithms and derivatives of logarithms to do that. The right side, however, has a y in it. And because it has a y in it, you have got to use implicit differentiation there to differentiate that. So you've got, my u would be y, and so it would be u prime over u. And so one way to write this is just 1 over y times dy dx. You could write y prime over y if you wanted to. That would be okay. I just don't usually write the prime notation. And so instead of writing y prime over y or 1 over y times y prime, I write 1 over y times dy dx. Always remember that when you differentiate in a problem where you're using this method, that when you take the derivative of the natural log of y, you will always end up with 1 over y times dy dx. That is using implicit differentiation and the chain rule. Definitely a chain rule problem, right? Where you have the natural log function of the y function. So the derivative of the natural log of y is 1 over y. The derivative of y would be dy dx. The right side is easy to do. The derivative of the natural log of x is 1 over x. So you have 3 times 1 over x. The derivative of x plus 4 is 1 over x plus 4. Remember, it's u prime over u. So it'd be 1 over x plus 4. And then finally, the last one, this would be 4 times 1 over x minus 5. U prime over u in that one also. And so you have 1 over y times dy dx is equal to 3 over x plus 2 over x plus 4 plus 4 over x minus 5. And then solve for dy dx. Remember, this is implicit differentiation, so you're going to solve for dy dx, and you have y times all this stuff over here, like so. And then what I would want you to do is, typically when you use this method, is I'd want you to go all the way back to x's. And so here, note that y is equal to x cubed times x plus 4 squared times x minus 5 to the fourth. So you substitute that in place of y here at the end of the problem, so that you just have x's and a function of x for the derivative. So this would be x cubed times x plus 4 squared times x minus 5 to the fourth times 3 over x plus 2 over x plus 4 plus 4 over x minus 5. Now this method, and so we got the derivative. I didn't say it was going to be easy, but it is, the differentiation is probably much cleaner than if you had tried to differentiate at the beginning. This method that I just used right here has a name. This is called logarithmic differentiation. And logarithmic differentiation is useful when you've got multiplication problems, division problems, and powers. In this case, I had powers and multiplication problems. And so it was a useful technique for that reason. And so logarithmic differentiation is a method, right, where you take the log of both sides of a function to take advantage of the properties of logarithms to differentiate. All right, so let's look at another example of that. All right, so let's say we have f of x equals x to the fourth times 3x plus 1 to the 5/3, all divided by the square root of 2x minus 1. Now, if you're going to differentiate that function like it is, that differentiation would be horrible. This differentiation is horrible. Right? You've got a quotient rule, and then inside the quotient rule, you have the product rule. Inside both the quotient and the product rule, you have the chain rule a couple of times. It's just a really nasty problem. We can make this easier. We can make the differentiation easier by using logarithmic differentiation. In other words, we can take the logarithm of both sides of the equation, the natural log of both sides of the equation. Okay, so what do you get here when you take the natural log of both sides? F of x, remember, is another name for y. So you have the natural log of y equals the natural log of this horrible mess right here. The square root of 2x minus 1, I'm going to go ahead and write that as 2x minus 1 to the 1/2. Really, 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 really nasty expression, but we can simplify this using properties of logarithms. So simplify using properties of logs. All right, so when you do that, you've got, and it depends on how good you are at this. You can streamline this process and kind of skip over some steps, and I think that's not necessarily unreasonable here, that what you will end up with is 4 natural log of x plus 5/3 natural log of 3x plus 1, right? It's an addition problem because that's a product in the numerator. And then minus, because we have a quotient in there, 1/2 natural log of 2x minus 1. Right? So we can use properties of logarithms, and I'm using all the properties there, product rule, quotient rule, and power rule to rewrite that logarithm. That's actually a much easier differentiation problem now. So now differentiate both sides implicitly, remember. So we differentiate both sides, and you get the derivative of the natural log of y, which is the chain rule. It's 1 over u times u prime. So you have 1 over y times dy dx is equal to, and this would be 4 times 1 over x plus 5/3 times, now be careful, it's u prime over u, so the derivative of the natural log of 3x plus 1, u is 3x plus 1 there. So u prime would be 3 over 3x plus 1. And then minus 1/2 times, and then the derivative of 2x minus 1 would be 2 over 2x minus 1. And the differentiation's done at that point. Really not too bad. So you have 1 over y dy dx is equal to 4 over x. The next term, the 3's cancel, and you get 5 over 3x plus 1. The next term, the 2's cancel, and you're left with 1 over 2x minus 1. So dy dx, solving for dy dx, we'd have y times this mess. And then I would substitute in place of y what y is equal to from the original problem. Remember, this is what y is equal to at the very beginning of the problem. That's what f of x is. And so I'm going to substitute that in place of y here at the end. I'm not going to worry about getting common denominators here. I am cruel, or I'm mean, but I'm not cruel. Maybe that's the way to say it. And so I would say that if you can get this far, you're doing great. And so I'm not going to worry about getting a common denominator with these fractions at all. You could also multiply through by that factor, and you can see how things cancel out, but I still would not ask you to do that at all. All right, we're doing good with logarithms here. Let's look at another way that implicit differentiation, besides logarithmic differentiation, might come into play. So let's say we have this equation, 4xy plus natural log of x squared times y equals 7. So if you were asked to find dy dx, I'd have to use implicit differentiation here. All right, and so you're going to differentiate both sides of the equation. But what would you do first? Again, you have a natural log in here. I would simplify that first. So don't jump into this problem until you can make sure that all your logarithms are simplified as much as you can get them, and then differentiate. So you have 4xy plus, plus the natural log of x squared plus the natural log of y equals 7. And so you'd have 4x plus y plus 2 natural log x plus natural log y equals 7. Now differentiate. Once again, I saw in the test, test 1 and with implicit differentiation, a lot of people would kind of overlook the fact that this has got to be a product rule problem to differentiate that, because it's a multiplication problem. So you got to really watch for that. So this would be the first factor times the derivative of the second factor. So the derivative of y would be dy dx plus the second factor, y, times the derivative of 4x, which is just 4. So this is 4y. Plus, let's see, 2 is a constant factor. The derivative of the natural log of x would be 1 over x. Plus, and then the derivative of the natural log of y, like we saw with implicit differentiation, this would be 1 over u times u prime. So 1 over y dy dx. And then that would be equal to 0. The derivative of 7 is 0. All right, so you end up with 2 dy dx terms and 2 terms that are not dy dx terms. So the 2 dy dx terms, this term here and this term here, going to keep those on the left side of the equation and factor out the dy dx out of those 2 terms. So it'd be dy dx times 4x plus 1 over y, like that, equals, and I'd move the other 2 terms to the other side of the equation. So this is going to get moved to the right side, that's going to get moved to the right side. So that would be negative 4y minus 2 over x. And then dy dx would be equal to negative 4y minus 2 over x, all divided by 4x plus 1 over y. All right, and then to clear fractions there, it's a complex fraction. If you wanted to clear the fractions out and simplify it, I don't usually like to leave complex fractions in an answer. I could multiply top and bottom by xy over 1 and clear out the fractions there so I don't have a complex fraction. So dy dx is going to be equal to negative 4xy squared minus the x's cancel. You're using the distributive property here to multiply this out. And so this would be minus 2y. And this would all be divided by 4x squared y plus 4x. Plus x. Like that. And that would be your derivative. Not really a convenient way to write it just as a function of x at all. And so you'd probably just leave it in that form like that. Okay, so that's a nice little implicit differentiation problem. All right, the next step here. We're almost finished with logarithms, not quite, but almost finished with logarithms. If we have f of x equals logarithm base 2 of x cubed plus 4x squared plus 1, like that. So this is a base 2 logarithm. And so remember, when you have a base other than e, you get that extra factor in there for the derivative. So, so recall here that in the case of logarithm base b of u, right, that the derivative, if that's y, that y prime is 1 over the natural log of b times u prime over u. So you get that extra factor of 1 over ln b in there, and then the rest of it's just like a regular logarithm as far as a natural logarithm as far as differentiation. So in our problem here, f prime of x, following along there, would be 1 over the natural log of b, so that'd be 1 over the natural log of 2 times u prime over u. Everything, so it's still the same basic idea as for natural logs. The only difference is you get that 1 over natural log of b factor at the beginning. So this is u prime over u, so this would be 3x squared plus 8x over x cubed plus 4x squared plus 1. And that would be it. There's really not anything else you could do with that. So you just leave it in that form. So, all right, so I wanted to point that out. Also, I do want to look at some examples of some expressions that involve exponents, where logarithmic differentiation might be of use to us. So for example, if you have f of x equals x to the x power. Now think about x to the x for a minute. You know, that's an exponent expression. If you have x cubed, if you have x to a constant power, well, f prime of x is 3x squared, right? And that's a variable to a constant power. And if you have a constant to a constant power, sometimes that just causes all sorts of crazy answers. But that's just a constant, so that its derivative is 0. And so those two derivatives, the power rule and 0, are come up right away. But this function doesn't fit either of those forms because this is a variable and a variable power. Now the other one we have to worry about is what happens if you have a constant to a variable power, like a raised to the x power. And we'll talk about that in a minute. So that example we still want to talk about. But let's look at x to the x. What I'd do is just use logarithmic differentiation here. So, whoops, not ready to differentiate yet. So you've got y equals x to the x. Take the natural log of both sides of the equation. And then bring that power down in front. And boom, now you're going here as far as how you can do this problem, because this is differentiate both sides. You're just going to have the product rule on the right side of the equation. So differentiate both sides. And in particular, this is going to be a product rule problem. So what do you have here on the left side? You get our familiar 1 over y times dy dx, right, using the chain rule. Right, it's the natural log function of the y function. And on the right side of the equation, we're going to use the product rule. So this is going to be the first function times the derivative of the second, but the derivative of natural log of x is 1 over x, plus the second factor times the derivative of the first. So that's just 1 times natural log x. And so you get dy dx to be y times 1 plus ln x. And y was x to the x, so you end up with dy dx to be equal to x to the x times 1 plus natural log x. Okay, so the moral to the story here is, on this problem, is that if you have a function that's in that form, if you have f of x is equal to a variable base raised to a variable power, like that, use logarithmic differentiation to differentiate that problem. Right? Use logarithmic differentiation. All right, so if you have f of x is sine x raised to the x squared power. So notice that that's an example of a variable raised to a variable power. And so this is a classic example of using logarithmic differentiation to evaluate a derivative of a function that's in this form. So you take the log of both sides of the equation. Right, so I took the log of both sides, the natural log of both sides. And then I use the power rule for logarithms, and I bring that x squared down in front. Now, please, please, please don't confuse natural log of sine x as multiplication. This is not multiplication right here. This is simply function notation, right? It's the log function, the natural log function of the sine function. So that's going to be a chain rule when we differentiate. So differentiate both sides. On the left side, you'd have 1 over y times dy dx. We've now seen that 4 or 5 times in the last 30 or 40 minutes. Right, we're differentiating the natural log of y. Equals, and on the right side, we would use the product rule, right? Because this is x squared times the natural log of the sine of x. So this would be the first factor times the derivative of the second factor. So the derivative of the natural log of sine x, right? Sine x is my u here, right? So this is going to be u prime over u. So that'd be cosine x over sine x. It's u prime over u. So that's the first factor times the derivative of the second factor. That's the derivative of the natural log of sine of x. Plus the second factor times the derivative of the first factor, but the derivative of x squared is 2x. All right, and let's see. There's a little bit of cleaning up you can do here. So dy dx is equal to y times x squared times, and cosine over sine is cotangent. So I'd probably write it that way. Plus 2x natural log of the sine of x. It's not the simplest derivative in the world at all. Certainly not. So dy dx would be equal to sine x raised to the x squared power times this mess in the brackets here. Like that. All right, so we know how to take care of a variable raised to a variable power. And so the last thing we need to do today is look at derivatives of exponential functions in the form b raised to the x power. So the first thing we're going to do is we're going to look at f of x equals e to the x, and we're going to differentiate that function, or find the derivative of that function. All right, so f of x equals e to the x, you know, if you wanted to, you could certainly use logarithmic differentiation here. And so you have y equals e to the x. You could take the natural log of both sides, like so. But wait a minute, this is the natural log of e to the x is inverse cancellation, because that's the log function of the exponential function. And so that's inverse cancellation, and those cancel each other out, and you're just left with x. So now differentiate both sides with respect to x, and you have chain rule on the left side. So that's 1 over u times u prime, or 1 over y times dy dx. That's our chain rule. Derivative of the outside times the derivative of the inside equals the derivative of x is just 1. So you multiply both sides by y, and something, what seems is kind of crazy happens. You get dy dx is equal to y, but y is equal to e to the x. And so notice what we've just done is we've just derived the idea that if f of x is equal to e to the x, then f prime of x is equal to e to the x. It's its own derivative. And using the chain rule to extend that, we have that if f of x is equal to e to the u of x, e to some function of x, then f prime of x would be the derivative of the outside, or the derivative of the exponential function. So that'd be e to the u of x. It would be itself times the derivative of the inside, which would just be u prime of x. So it'd be e to the u times u prime. Definitely want to shade that. That's our other big idea here with exponential functions then. All right, so we've just derived that the derivative of an exponential function is its e to the x is itself, and then the derivative of a e raised to a power is the function itself times the derivative of the exponent. So if we have f of x equals e to the x squared minus x power, right, so that's e to a function of x. And so our derivative, using this property that we've just derived, would be e to the u times u prime. So f prime of x would be the function itself times the derivative of the exponent, which would be 2x minus 1. And that would be it. That's all you would need to do. That's not too bad. If f of x is e to the sine of x power, then f prime of x would be e to the u. It would be the function itself, e to the sine x, times the derivative of the exponent. And the derivative of the exponent here would be cosine x. And to be honest with you, there's really not anything else you could do with that. You could just leave it in that form. F of x is e to the x plus e to the negative x. It's a common kind of form that you're going to encounter. Then the derivative of that function, well, the derivative of e to the x would be e to the x. And the derivative of e to the negative x would be e to the negative x times the derivative of the exponent, which is negative 1. So notice all that does is change the sign. So f prime would be e to the x minus e to the negative x. If f of x was e to the 3x plus e to the negative 3x, then f prime would be the derivative of e to the 3x, which would be the function itself, times the derivative of the exponent. The derivative of 3x would just be 3. And you'd have the same situation with the next term. You get the function itself times the derivative of the exponent, which would be negative 3. And so that would be my derivative right there. If you wanted to, you could factor out the 3, and you'd have e to the 3x minus e to the negative 3x, like that. All right, so that's not bad at all. All right, let's, we're not far from being finished here. Next example, let's look at f of x equals e to the x plus e to the negative x, because we now know how to take the derivative of that, divided by e to the x minus e to the negative x. All right, unfortunately, there's not really any properties of exponents that would allow you to simplify how you wrote that. You could use logarithmic differentiation here, but it's really not going to help you all that much to use logarithmic differentiation, so I'm just going to use the quotient rule directly. Logarithmic differentiation is really not going to help because you have addition and subtraction problems in there, and logarithmic differentiation doesn't really help with that. So f prime of x would be the bottom function times the derivative of the top function, but the derivative of e to the x plus e to the negative x, we just did that one, is e to the x minus e to the negative x. All it does is change the sign, minus the top function, e to the x plus e to the negative x, times the derivative of the bottom, and again, all that's going to happen there is the sign is going to change. And that'd be all over the bottom squared. Now you have this kind of nasty expression in the numerator, and there's a couple of ways you could look at that. You don't really have a common factor in there, so you really can't factor anything out. So what I would do there probably is there's a couple of ways, creative ways to multiply this out, but I'd probably just use the good old-fashioned FOIL method and multiply it out. So now remember, e to the x, let's put this in a different color at the top here. Let's say you have e to the x times e to the x. Well, remember how you do that. You just add the exponents, so that's e to the 2x. So if you have e to the 2x times e to the negative 2x, notice if you add the exponents, you get e to the 0, which is 1. So kind of keep those things in mind when you're multiplying this out. So using the FOIL method, using the good old-fashioned FOIL method, you have e to the x times e to the x is e to the 2x. Outside 2, e to the x times e to the negative x would be minus e to the 0, which I'll write as 1 in a minute. Inside 2 also gives you minus e to the 0. Last 2 gives you plus e to the negative 2x. And then on the second multiplication, since it's subtraction, every term is going to be negative. So you have e to the minus e to the 2x, minus e to the 0, minus e to the 0, minus e to the negative 2x. Yuck. And that'll all be over e to the x minus e to the negative x, quantity squared. And if you go through all that, the algebra in there and everything, the e to the 2x's add to give 0. And the e to the negative 2x's add to give 0. And then what about all those e to the 0's? Remember, e to the 0 is equal to 1. And so you end up with 4 of those in there. And so you end up with the numerator just being negative 4 over e to the x minus e to the negative x, quantity squared. Maybe kind of unexpected that you end up with a constant in the numerator there on that problem. So, so that was kind of a messy problem there. Now, so let's look, finally, kind of finish this up. What if instead of e to the x, you have a raised to the x, where a is positive, certainly, but the base is more general. It's just written as a, so it's not necessarily e. A is just any positive number there. So this is a problem where you use logarithmic differentiation. So y equals a to the x. Then take the natural log of both sides of the equation, like so. Bring the x down in front. Now remember, on the right side here, the natural log of a is a constant, because a is a constant here. So the natural log of a is a constant. So don't think that that's the product rule on that side of the equation. When you take the derivative here, you get 1 over y dy dx. About the 6th time we've seen that now. Equals, and then on that side of the equation, the derivative of x is 1. And so you just have 1 times natural log of a. Natural log of a is a constant. It just comes down for the ride. And so dy dx is equal to just y times natural log of a. Y is equal to a to the x, and so dy dx is equal to e to the x natural log of a. I'm sorry, not e to the x, I apologize, a to the x. So what I want you to do is compare e to the x in the more general statement, a to the x. If f of x is equal to e to the x, then f prime of x is just e to the x. If f of x is equal to a more general statement, a to the x, where a is greater than 0, then f prime of x is a to the x natural log of a. The property for e to the x is just a more specific version of the second property there. It's for the, in particular, where the base happens to be e. So notice that when the base is e, you actually have a simpler form for the derivative than if the base is something else. So if f of x is e to the x, then f prime of x is e to the x. If f of x is 2 to the x, then f prime of x would be the function itself, 2 to the x, but it'd be times this extra factor, natural log of 2. If f of x is 5 to the x, then f prime of x would be the function itself, 5 to the x, times the natural log of 5. You get that extra factor in there. All right, so kind of summarizing exponent expressions then, as far as derivatives. So let's kind of summarize this. So exponent expressions. So if you have f of x equals a to the a, that's just a constant, right? And so f prime of x would be 0. If f of x is x to the a, that's a power rule problem. And so f prime of x would be a times x to the a minus 1. That's just a simple power rule. If f of x is equal to a to the x, that's what we just derived on the last page, then f prime of x would be a to the x times the natural log of x. And then, the specific version of that property for e to the x would be that this is just e to the x, because the natural log of e is equal to 1, so that's just a specific version of that property. And then finally, if we have f of x equals x to the x, or in general, a variable to a variable power, then use logarithmic differentiation in that problem. Right, and go that route. All right, so that's probably a good summary of everything we've done with exponent expressions. All right, so we have got, let's see, one more problem I think maybe to do, and then we will be finished with this. So if you have, let's look at one more example. Let me flip the screen here. And this will be our last example of the day. Let's say we have e to the xy plus x squared minus y squared equals 10. All right, so this would be an implicit differentiation problem. All right, so this is implicit. So using implicit differentiation, we take the derivative of every term separately. And that e to the xy, that's going to be the chain rule problem. It's the exponential function of the xy problem, of xy function. And then in particular, xy is going to be the product rule. So the derivative of the outside, the derivative of e to a power is just itself. So this is e to the xy times the derivative of the exponent, and that's the product rule. So this is x times dy dx plus the second times the derivative of the first, which is 1 times y. Like that. So that's the derivative of the outside. You know, if you want to write it out or think about it that way, you certainly can. So this is the outside right here. And this is the inside, is this product rule right here. And that inside, in this case, is the exponent. Right? You're always multiplying by the derivative of the exponent. All right, and then this is plus x squared. The derivative of x squared is 2x. Minus y squared, so the derivative of that implicitly would be 2y times dy dx. Chain rule again, derivative of the outside times the derivative of the inside equals 0. So that's differentiating through that equation. And then, you know, what I'd probably do here is use the distributive property and multiply this out. So, because you're trying to solve for dy dx. So you have e to the xy times x dy dx. So that's x e to the xy dy dx plus y e to the xy plus 2x minus 2y dy dx. Right, so you first multiplied through by e to the xy there because I need to get that dy dx out of the brackets there. And then I have two dy dx terms. There's a dy dx term and there's a dy dx term. So I factor out that dy dx out of those two terms. We have x e to the xy right here minus 2y. Close off the brackets. Move the other two terms to the other side of the equation. So you have minus y e to the xy minus 2x. And then finally divide both sides by what's in the brackets. So you have negative y e to the xy minus 2x over x e to the xy minus 2y, like that. And that would be our derivative. Couldn't really put it in terms of just x easily, and so that's how we'd leave it. All right, so we have now covered all of Chapter 3. We've talked about derivatives. We have also covered section 4.1 on related rates. And so you should be working on homework to get yourself up through at least 4.1 right now and starting to think about getting exam or homework 3 finished. And you know, that's not due this week, but next week. And we're also starting to think about exam 2, where the review for exam 2 will be coming out next week sometime. And then the exam window, testing window, will be starting 2 weeks from tomorrow, in fact. All right, so please practice. Come by for online office hours. Remember, I have online office hours tonight from 8 to 9. I also have online office hours Sunday from 7:30 to 9, Monday 8 to 9, Tuesday 8 to 9, Wednesday 8 to 9. So definitely come by for help. I also have online office hours tomorrow for this class from 1 to 2. So please take advantage of those online hours. Come by for help. Email me if you want your graded exam 1 sent back to you. Remember that I've posted those test grades on D2L, so go to your D2L site for this class, and you should be able to find your grades there. Have a great day, and we'll be in touch. Thank you.